Right. Hello. I'm going to make this video, which is about how to make a finite element model of a fractal fixation construct. I found that it's not so straightforward, so I want to share my the process I developed with others. So I'm gonna call this a fractal fixation construct. I'm creating the model. Right. I just want to say that the fractal fixation construct, what I mean is, so I'm going to model a plate fixed to a bone. Normally you use this when a bone fractures, but here I'm not going to model the fracture itself because I'm analyzing a case after the bone has already healed. So I'm going to model a bone with no fracture and the fractal fixation plate on it with some screws which are actually going to be part of the plate, but we'll see that later. Okay, so I'm going to start with the bone. Name it here. You can change different things. I'm going to keep it just an extrusion. Okay, so to start with, I'm going to make the outer diameter of the bone. So this is going to be 17.5. This is actually the radius, sorry. So I want the diameter to be 35 millimeters. By the way, Abaqus has no units as such. You just have to be consistent with whatever you use. So if you assume this to be millimeters, you have to make sure that your stress is in the right units to work with this, right? Okay, so then we're gonna make another circle here, and I want that to be 13.5, and that is because I want the cortical thickness of the bone to be 4 millimeters. All right. The next thing I'm going to do is I'm going to fix the center of these circles because otherwise they start moving around when I change things, and I don't want that. All right, so that's it. I'm going to now set the depth to 300 millimeters, which is the length of the bone that I'm considering. Of course, these dimensions change given whatever bone that you're considering, and I'm assuming this is in the diaphysis in the middle of the bone where it's sort of like a tube. Of course, if you have a more complex bone, then the whole thing becomes a bit more complex. And in fact, in the diaphysis, it's also a bit more complex in reality. But I'm simplifying it to be a tube. I'm going to model the implant. Again, just an extrusion. Again, I'm going to make a simplified implant, starting with diameter, the outer diameter of the bone, because I want it to be right at the surface of the bone. And so I'm going to make this again, 17.5, right, radius. And then I'm going to set the outer diameter of the implant to 21.5, such that the thickness of the implant is going to be 4 millimeters, right? Now again, I'm going to fix this middle of the circles, and I'm going to move these guys here, like in the case of the bone. Now, of course, this would be another tube, which is not what we want. Instead, we want a plate, right? So for that, I'm going to cut this sketch. What did I want to do? Yes, so I want to make construction line here so that I can dimension this. So I want to give this an angle. Oh, wait. Sketching in Abaqus is not so simple. I first tried to do it with first sketching in SolidWorks, and importing the model here. But it turns out that when you want to change things to check how you're varying certain parameters of the implant, varies other things, it's a bit complicated if you have to change it in SolidWorks and then import it again. So it's easier if I just do it all here. Okay, so you can set this to whatever you need so that the width of the implant is what you want. I'm going to set it to 40 degrees for now. Okay, now the next thing I want to do is I want to mirror that. All right, first let me find out again where the mirroring is. Here it is. So now it asks you, in Abaqus, you have to always click one thing and then OK, and then a click and then OK. So you have to make sure, always check this bottom thing here, messages. So it says select the type of mirror operation, and I want to copy that. So I select this, then I select the mirror line, and then done. Oh no, that didn't work. That's not what we want, right? Okay, so I go back. And I'm going to try that again. Select the type of mirror operation, copy. I know, you first pick the mirror line, and then the entities to mirror, and then done. And that works now. Okay, now I'm going to trim. So I'm going to go on auto trim. And I'm going to trim these sides here. And that should be all now, right? Although it seems that the dimensions of these two are now gone. So I want to just set them again. Okay, so now it's all ready. So that's gonna have a depth of 150 millimeters, half the depth of the bone. Okay, so I have two parts now, right? I'm gonna assemble it together, even though I need to do other things as well. But I'm gonna just start by assembling them together. So you double click on instances, and then you just select them both. Okay, so you just say okay for now. And now what I want to do is I want to put this implant in the middle of the bone. So for that, I'm going to move the implant to translation, and then it asks to select the instances, done. Then select the starting point of the translation, and I want to move it to the middle. So intuitively, you would want to select the end point. So start point is there. So this is 75 millimeters, should be half the implant, and that's what I want because you want to put it in the middle. So that should be fine for now. Okay, so now I'm gonna go back to my bone. No, sorry, I'm gonna make some materials, right? So I define the materials first. So first you create the materials. So I think someone could make this a little bit more more user friendly, but anyway. First I'm gonna create the bone material. It's called cortical bone, right? You should notice that I'm not modeling the inside of the bone, which is the I'm only modeling the cortical bone, right? So I'm not modeling the soft tissue inside the bone, which is more like callus. It's more like cartilage, less stiff, right? But this is stiffer. This is elasticity I found is usually a Young's modulus. I'm modeling as isotropic, all very simplified, isotropic, elastic, linearly elastic. What it means that it's elastic is that it conserves all the energy. So if you're looking at a stress strain graph, it would be a straight line up. And isotropic, it just means that the properties, so the Young's modulus is the same in all three of